Swayam Prabha. Digital India. Educated India.
Collection of smaller meshes.
Right. So big mesh can be thought of as consisting of smaller squares. Each of these small squares has a kind of a random variable as the answer. It's not completely random, but within some range it gives you the percolation threshold. But we need to cover all possibilities, and it so happens you can take these squares and you can jumble them. Sometimes this particular square, one possibility will appear in one experiment, it will appear in the top left. In another experiment, that same square will appear in the bottom right, and you will simply be permuting when you repeat the experiment. Essentially the same units will be there, subunits. So in one experiment, this subunit with 0.54 percolation threshold was there, and you did the whole experiment on the larger square. The next time you did the experiment on the larger square, this would have appeared at a different position. The same squares go on permuting in that larger square, and that's the reason we end up with a definite answer when we work with a larger square. So this important concept of percolation threshold is, it has a well defined value for an infinite system or a system with very large number of elements, and it's a random variable for a finite system. We will remember this because I will come to this point later in the talk. And this is this paper I was referring to, Conductivity in Two-Dimensional Site Percolation Problem by Watson and Leith. I just wanted to show you, you must have attended talks here where very sophisticated equipment were used. I wanted to emphasize that's not necessary. Read this part. The coordinates of the sites to be removed by hand with wire cutters were provided by a standard pseudo number generator, and the conductivity was measured with a digital voltmeter, something you may have in your home, and a constant current source which was calibrated against a standard resistance. This is all the experiment that went into it, but a brilliant idea which they were able to completely explain what was going on. And these are pictures from the paper. As they go on cutting, they used to take a photograph of what is cut, what is intact. From the photograph, they can infer how much has been cut. The sitting and calculating might be hard. And then they measured how the conductivity goes on decreasing as the fraction of sites are removed. And then they hit this number 0.41 because they are plotting with the sites removed, not the sites intact. And then the conductivity, it's a measure of how much the current flows. It's inverse of the resistivity actually. And then it goes to 0, that means no current moves in the system when it is 0.41. Now we look at a different problem, because I mentioned this idea of percolation percolates the entire domain of science or the domain of knowledge. It appears in every field that you can imagine. And this a different field, magnetism. You are in class 12th, so you must have learnt a little bit about magnetism, that there is some idea of spins. You can think of these spins which are there with the atoms like tiny compasses. This is the compass which responds to the magnetic field. I have tried to depict that pictorially. A bar magnet is an external magnetic field which causes the direction of the compass to rotate because the compass responds to the magnetic field. But then, what are the ways to produce magnetic field? One concept is a magnetic moment. If you have a tiny current loop, that's a magnetic moment which can respond to the magnetic field, which can align with the magnetic field. And in materials, these tiny currents may be there, which may be the source of some kind of magnetic behavior. and when you apply a magnetic field, it will try to align these moments with the direction of the magnetic field. There is this quantity which is very mysterious called the spin or an intrinsic magnetic moment. What do you know about spin? Yeah, that's the only thing which is not true about spin. I tried to depict it that way, but I have put a cross here, like that's not it. Spin is some kind of intrinsic magnetic moment, which if initially people thought the electron is spinning about some axis and that is producing, the charge going around is producing a magnetic moment, which is the spin moment. But then their calculations, which were based on the size of the electron, and if you plug that in, you will get a velocity of motion on the surface which exceeds the velocity of light. So all we can say is we don't know how spin originates, but we can measure it. It responds to the magnetic field, and it is not this simple classical picture of a spinning electron. Spin is anything but that. And these spins are also like small compasses. If you apply a magnetic field, they'll respond to it. But more than that, they also affect each other, and that interaction is mediated through electrons, the outer electrons of the material system. Sometimes that interaction favors them to align with each other. That's called ferromagnetic interaction. Sometimes that interaction may favor opposite alignment. That's called antiferromagnetic. Various kind of magnetic orders are possible. Let's stay with ferromagnetic, which means then there are spins on a lattice, and if temperature is low enough, because temperature tries to randomize them, then they will all be pointing in the same direction. This is called a spontaneous magnetization, and you are all familiar with this. Iron is one example of spontaneous magnetization. It shows this ferromagnetic property. And how much is the magnetization? Well, each of this has some magnetization, some unit of that, and then n is the numbers of them which are magnetized in that direction. We can talk of a net magnetization. Let's say some of them are up and down, then how many are up, how many are down, so take the difference. In a simple toy model, you can say this much is the magnetization. Here is the situation on a cubic lattice. These are atoms, each of this atom has a spin, all of them are aligned in one direction. So it's like the perfect situation. It has large magnetization, highest possible. It could not have been more than this. Next we look at a situation where you take atoms of a ferromagnet and atoms of a non-magnetic material and mix them and see under what situation it still retains that property of iron or property of magnetism. And we can depict it as follows. This is all happening at atomic level. This is one iron atom. This is some non-magnetic atom. Let's say we put silicon or copper or something which is having very little magnetism. Then again an ferromagnetic atom. The open circles are ferromagnetic, the black filled circles are non-magnetic. They have been distributed in random manner because I just took iron, this atom, maybe I heated them to high temperature, they formed an alloy and then they just got random, and then I quickly cooled them so that they could not settle into the right positions. They formed a cubic lattice, but it was all random. And here we can see the idea of what is a cluster. This is a cluster of ferromagnetic atoms. It has 1, 2, 3, 4 such ferromagnetic atoms. This is a cluster of 2 and a cluster of 1 are also shown here. The reason I have depicted all these 4 to point up, all these 2 to point down and so on is because if there is a nearest neighbor, it tries to align the atom, the neighboring atom. All try to align in the same direction because their interaction favors alignment, being parallel. Just like two small compass, though they don't actually do it, but think of two compass which like to align each other. When you bring them close enough, they might align each other. Then this is a far away distance, you see. if this distance is a, the side of the square, this is root 2a. That's large enough that it can't influence. So randomly the directions in the other clusters would be different. This cluster has a unique direction all up, whereas this one is root 2a, a far away distance, and it has to the left, something has to the right, and so on. And if we take the average, it is a very small number, because sometimes the magnetization is to the right, to the left, to the top, to the bottom. What's the average? Something close to 0. Yes.
What determines that separate atoms direction of point?
Right. What determines, maybe your question is why they are up and not down. Is that the question?
No, it is singular, right? Why is it not detected? What determines that direction when it's singular?
Are you referring to one cluster?
No, not a cluster, sir. Separate.
Okay.
How about the cluster?
Out of, so why these are up and this is side, is that the question? Huh? So whether it is side or up or left or down, all have the same energy, equal energy. So with equal probability, it can be in any of these configurations.
What is determining that?
Some random process, a small perturbation, small disturbance to the system. Okay. Even you can take a very simple example where, if I can go back to answer your question, here all of them are depicted up, and we can ask the question why all of them are up, why not all of them are down. Now with equal probability it could be this or that. The physics that says is they should point in the same direction, but which direction we don't know. Unless we disturb it with an external field. I can apply an external field and cause them all to go up. But if I did not apply an external field, then small perturbations will force them to take up any one direction, take a stand. Let's look at these magnetic clusters. Like here, all of them are non-magnetic. Now I have brought in some magnetic atoms, and you can see this is a cluster of 3, this is a cluster of 2, a cluster of 1. The same thing depicted on another picture, just for clarity. Now let's call X as a fraction of magnetic atoms, which is now similar to X was the fraction where they were conducting the electrons in the previous problem. And if X is very, very small, that is, there are isolated magnetic atoms completely surrounded by non-magnetic atoms, and each of them will have a random direction. So the net magnetization is, intuitively it should be 0. If I increase X as depicted in the previous graph, let's see here, this has some larger X, some clusters start to form, a cluster of 3, a cluster of 2, and so on. Finite isolated clusters. Again, the direction is random and the net magnetization is close to 0, or it might be a small value in a finite system, but in a large enough system it will be close to 0. And then you go beyond a certain threshold value, this very interesting nomenclature comes in. It's called infinite cluster, something which has infinite size. Now, are we really working with infinite samples? We are not. Infinite cluster means if you increase the size of the system, the cluster also grows with it. There is no limitation to how big it can be. That's an infinite cluster. And here you get oriented magnetization, which is non-zero. Shall I go ahead? This is an example of infinite cluster. All of them like to align each other. There are very few non-magnetic atoms, and here sits just one single magnetic atom pointing in the opposite direction. So M is really not at its maximum possible, but the size of the cluster is really infinite. It permeates the entire space. The entire system can be thought of as having a finite large magnetism. So what are the characteristics of this infinite cluster? It's a single permeating cluster. Any system can have only a single infinite cluster. It permeates the entire system. There can be other clusters which are smaller. And then this mathematical expression conveys the idea of infinite cluster. There is a system with a maximum number of atoms belonging to that cluster. And capital N is the total number of atoms in the system. If you increase the total number of atoms in the system while maintaining the same fraction, it's above the percolation threshold, this many percentage are magnetic, then the size of this cluster also keeps on growing. If we could in principle make an infinite size ferromagnet, then the cluster will also be infinite size. And this is equal to Px, which is the fraction of atoms belonging to the infinite cluster. It's simply determined by how many atoms belong to the infinite cluster, the fraction, which is a non-zero number if x is more than xc. If it's less, infinite cluster does not exist. Some cluster may form, but then you keep on increasing the size of the system, you will find that it has disappeared. In very small systems like 2 by 2, you can easily form a cluster, or 3 by 3, you can easily form a cluster, but it won't grow. Yes. Sorry? Yeah, I have not proven that, but it can be shown. I have not shown it in this talk, that only one infinite cluster can exist in the system, like it has been depicted here. A system can have one such cluster where if you keep increasing n, the size of that system upon n keeps a constant value. Total number of atoms is increased, you maintain the same fraction, and the size of that cluster also increases. But there could be other clusters whose, say, n max prime, if I can call it, the next smaller cluster, second smaller cluster, that if you increase the size and take the ratio n max prime upon n, it will tend to 0 as n tends to infinity. All other clusters become smaller in proportion to the system size, so it's upon n. They don't grow, whereas one infinite cluster keeps on growing above the percolation threshold. How do these two different problems relate to each other? One problem was about magnetism, another was about conductivity, and is there a connection between these two? What do you think? Is there a connection? Are these describing the same problem? But our interest is not how magnetic field is produced, but when these clusters form, infinite clusters form, when the percolation threshold is achieved. There is a percolation threshold in both systems. So can we say that we have just described two identical problems in slightly different languages? Do you get the feel? Right? And this picture can help you appreciate that point. The same sites are here, the ones which are electrically conducting on the right hand side, and the same sites are magnetic on the left hand side. And you can see if we could apply voltage within a single cluster, current will flow, but across two clusters current will not flow. Once an infinite cluster forms, end to end current will flow. Here there is magnetism within a single cluster, and there are many clusters, but they don't talk to each other. If you look at the magnetism as a whole, there is no magnetism, there is no current. So there are a lot of things in common, although there are differences. I will point out the differences in the second part of the talk. Here again, two different clusters, you apply a voltage, there is no current. Yes.
Sir, so in the electrical one,
Yes.
will the cross ones still form? Because there it's shown as if they are connected, but
Are you referring to whether these will form there will be current between them? They are blocked, that's a different cluster. There is no wire linking them. The cross point of the wire has been removed. Right? Current has to flow either on the left arm, right arm and then go up, or go up and then go to the right, but both are not possible. Okay, one more, yeah, please tell me. Okay, why is I equal to 0 in this diagram? If current had to go from here to here, what are the possible routes? It can go directly from here to here, but this site is removed, it's open. Or it could come down and then go here, but that's also not possible. It's all these three are removed. It's just air gap there. And it could go to the top and then come here, but that's also removed. So there is no way that current can go from this end to this end when you apply a voltage. Well, this from here the current can go nowhere. It can't go to the left, it can't go to the top, to the right and to the bottom. All neighbors are cut off.
Setup, it is connected to wires, so if it's not connected diagonally to wires, it cannot connect. But what about the magnet?
Yes, that's a good question. In fact, I will address that question in a second part of this talk. But now we have assumed that there is a nearest neighbor interaction, which means that two spins can align each other if they are separated as nearest neighbors a distance a. And if the distance is large, which looks very intuitive, things which are far away have lesser influence on each other. The interaction weakens, and very commonly you will find in physics this nearest neighbor interaction. In a later part of the discussion, I will relax that assumption.
So in the magnetic diagram,
Yes.
second last row is upward pointing.
Right.
But then
Yeah.
But then there is also another cluster which is also pointing upward.
Yeah.
So
You're saying this is the cluster that points upward.
yes, that's a cluster that points upward, and then there's an individual thing that's
Yes.
pointing upward. So do we consider the entire thing to be part of the
They are
same
two
cluster?
different clusters, but there's always a chance that they may point in a same direction.
So if they're diagonally located, then they can't be part of the same cluster.
No, they are not part, because only the nearest neighbors can be part. There is still a chance that it may point in the same direction. These are some differences with the electrical problem. The electrical problem, there is absolutely no current, but here there is a chance that it could point in the same direction.
Okay.
And then when people made a plot of this, that is a plot of conductivity normalized to the original conductivity as a function of how many sites are intact, right? And here how many sites are removed, because if sites are intact, conductivity should be high. So this is where all the sites are intact. The problem can always be defined in two ways, either in terms of blocked sites or in terms of non-blocked sites. So here all the sites are available, that is x equal to 1, yeah, that is it. And then you go on removing the sites along this path. So we are working with the same definition. You go on removing and then you reach xc, which is 0.59. After that there is no conduction. And working with the magnetic problem, you have px, which also has the same percolation threshold, but the curve follows a different path for reasons we will discuss later. Yeah, so we are also starting a new topic here, so it's a right time to have a break, 5 minutes. You can go for restroom or water or something.